Okay, let's look at a brand new topic today, counting. Okay, this is chapter 10. And counting on the one hand seems pretty easy because we're just counting things. 1, 2, 3, that's very basic. But counting problems can be very subtle, and it's very easy not to take everything into account and therefore to get the wrong answer. And this is an example of a counting problem which I remember from high school. This was a statewide test that was given as a math challenge, and I ended up as a sophomore winning the award for my school. And I remember this was one problem I happened to get right. I got a bunch of them wrong, but this one I got right. Okay, I think my high score for the school was 40, and that was maybe out of 100. So they were all kind of tough problems. Anyway, here's this problem. You've got all these little cubes. Okay. Each cube is a little unit cube, and you take these things and you pile them. You put 10 in a row, and then you put 10 rows to make the base. So the base of this big cube is 10 by 10, which is 100. And once you have the base, then you also make it 10 stories high. So it's 10 by 10, which is 100 times 10 is 1,000. So there's 1,000 different little cubes in this big cube. So you stack them all nice and tight together. Once they're all tightly stacked together like that, placed next together, then you paint the whole thing red, okay? Color of my shirt here, Davenport red. You paint the whole thing red, and when I say the whole thing, the outside of this big cube, you paint it red, and then once it's all painted and dry, then you pull it apart. You pull it apart, and then you ask how many of these small cubes have red paint on them. Okay, maybe just one side, maybe a couple sides, whatever, but they at least have one side of red paint. How many of these cubes, when you look at them, have at least one side which has red paint on it? Okay, so that's the question. So here's what I did. Okay, I said, well, let's think about it. All of these squares, cubes on the very front, there's what, 10 by 10 of them, there's 100 of them. You're painting the front, so all of those 100 of them have red paint, and that's going to be true for each of the 6 sides, right? There are 4 sides around the side of this cube, and then there's the top and the bottom. So you have 6 sides total, and each one of those has 100 cubes, and so that gives you 600 cubes, at first thought anyway, that would have that red paint. But then once I did that, I thought, wait a second, I've overcounted. Because I want to count just exactly how many cubes there are, and I notice that some of these cubes I've counted twice. Okay, so here's a cube right here, for example. I counted it as part of the front, and I also counted it as part of the side. So I counted this one twice, but it is just one cube. See that? So I need to get rid of all these that I've counted twice. So how many have I counted twice? So all the ones around the edge I've counted twice, and so how many edges are there? There's 1, 2, 3, 4 around the side of it, 5, 6, 7, 8 around the top, 9, 10, 11, 12 around the bottom. So you have 12 edges, each of those has 10, and so that's 120. So you take your 600 and you subtract your 120, and it seems like that would then be the right answer. But then I thought some more, and I thought, wait a second, it's still not right. So these have all been counted once. That's what I wanted. These along the edge have been counted once because I initially counted them twice, but then I subtracted them. But notice these corners. Okay, these corners. Each of these corners I counted 3 times, right? I counted as part of this face, I counted it as part of that, and I counted it as part of that. So I counted it as part of these 3 surfaces, so I counted it 3 times. But then I also subtracted it 3 times. I subtracted it as part of this edge, as part of this edge, and as part of this edge. So I added and subtracted it each 3 times, and so by the time I'm done, I haven't included it at all. So each one of these 8 corners I need to add back in so that I include them exactly once. So by the time I do that, I'm at 600 minus 120 is 480 plus 8 is 488. And so that was my final answer. And I only found out later there was an easier way to do it. If you think of painting this whole thing and then just pulling off all of the layers that have paint on them, that would be, there's, you know, layers on the two sides. Here you have layers on both of theirs, and here you have a layer on top and the bottom. You're going to end up with something which is not a 10 by 10, but which is an 8 by 8 by 8. Agreed? Because you're pulling one off the front, one off the back, that leaves you 8 this way. One off the top, one off the bottom, that leaves you 8 going up and down. And one off of each of the sides, which leaves you 8 along the front. So by the time you get, these are all the ones that don't have any paint on them, and that would be 8 times 8 is 64. If you multiply that by another 8, you get 128, 256, 512. So there's 512 of them inside which don't have paint. Since you started with 1,000 and you have 512 of them inside that don't have paint, that means you have 488 of them along the outside that do have paint. So anyway, it shows, I like this problem because it shows there's multiple ways of solving problems, and it also shows that you have to be really careful as you count, because it's easy to miss, to not take something into account. You have to be really careful with your thinking. So very good. So now I'll get rid of this one. Oops. In general, when you want to count, you multiply a lot of problems anyway. You multiply the possibilities. So say, for example, that I'm going out for the evening and I have 3 ties and I have 4 what do I have? Pairs of shoes? 4 hats, and I have 2 pairs of shoes. People don't wear hats much anymore. Let's say 4 shirts and 2 pairs of shoes. Okay? So given that any of these ties will work with any of the shirts and will work with any of those pairs of shoes, what are all the possible ways, assuming that everything else is the same, I'm going to wear the same pants no matter what, same socks, same underwear. What are all the possible ways I could leave the house? So you think about it, you've got three ties, and each one of those ties you have 4 shirts, and now that you've got your tie and your shirt, you still have 2 pairs of shoes. So how many combinations do you have in all? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4. 24, which you easily see you get by just multiplying these together. 3 times 4 is 12, times 2 is 24. So that's the total number of possibilities you have that you get by multiplying. Okay? So with that in mind, let's do a favorite problem of mine. I call it a license plate problem. Suppose that these are the characters that we have to work with. You have 11 characters. Actually, there'll be letters. A, B, C, D, E, F, G, H, I, J, K. I think that's 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So those are your 11 characters. And given those 11 characters, we want to make license plates with 7 characters. So we want to make license plates with 7 characters. And let's say that it's okay to repeat. It's okay to use a character more than once. Okay? So, how many choices do we have for this first spot? Do you agree that I have 11 choices? And once I filled that first spot, just like the ties and the shirts, now how many choices do I have for the second spot? Well, if I choose a C here, I can still choose a C or anything else there, and I can still choose anything I want there. So I've got 11 choices here, and I still have 11 choices for each of these things. And so by the time I'm done, I've got 11 to the 7th power, which I think I calculated, is equal to 19,487,171. Okay, so those are if you wanted license plates for every car in the state and you wanted to use just those 11 letters and you could repeat, you could have 19 million license plates. Okay, that's quite a few with just 11 letters. Okay, so now let's contrast that problem with the same problem, but now we're going to have these 7, and again we're going to have 7 characters, but now no repeats. Okay, you can't repeat. So, again, let's think about it. I choose something here. What do I choose? Maybe I choose an H. Point is, I have 11 choices. 11 choices. I was just about ready to make an H there. 11 choices for what goes in there. Now that I've chosen one, say an H, how many choices do I have for the second spot? I only have 10 choices now, so I choose one of them for that. Maybe that was the I, just to keep things easy. So now H and I are gone. How many do I have now for my third? Okay, whatever I chose here, I now have 9 choices here. Then you can see 8, 7, 6, and 5. Okay? So you multiply all those together, and you get, I'm kind of surprised, you get only 1,663,200. Okay? So look at there, we went from 19 million to 1 million just by decreasing these one at a time. I would have thought this would have been maybe half of this number, or no, it wouldn't have been half, but maybe a third or something like that. But anyway, it's just a small fraction of that. Okay, so there's the number. Now I want to show you something about another way of writing this number. This comes up quite often in mathematics. You have something like 5 times 4 times 3 times 2 times 1. And you multiply them all out, and that comes up often enough that we have a special name for it. We call that 5 factorial. There's the symbol for factorial. It's the exclamation mark, okay? So 1 factorial would be just 1. 7 factorial would be as you expect. 7 times 6 times 5 times 4 times 3 times 2 times 1. So that's 7 factorial. It turns out, notice they all stop at 1. They all stop at 1, so it wouldn't even make sense to talk about 0 factorial, you would think, because these all are some number larger than 1 going down to 1. But it turns out that it's very convenient, for reasons that I don't think we'll see it in this chapter, but you see it throughout mathematics, to define this to be 1 as well. So nothing that really applies to us here, but just so you fully have the definition, that's defined to be 1 as well. But anyway, so that's factorial. So notice that using the factorial, I could have written this as what? 11 factorial divided by 4 factorial. Do you see why? Because 11 factorial is 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And now you're dividing it by 4 factorial, which is 4, 3, 2, 1. And so those divide out. And you just end up with this left. See that? So this thing right here, if I wanted to, I could write it like this. And now, if I want to make it look even a little more complicated, I could say, oh, this is 11 factorial divided by, what's the significance of 4? why did I end up with 4 here? Notice it's because we have 11 characters to start with, and I had 7 blanks to fill. And so that's why we ended up with 4 down here. And so this is 11 minus, how many blanks were there? 7 blanks to fill. 11 minus 7 factorial. Do you agree? 11 factorial on the top. 11 minus 7 is 4. There's your 4 factorial on the bottom. If we had 8 to fill here instead of 7, then I would have had 3 factorial on the bottom, which would have been 11 minus 8. See that? So there you have it. So that's that. And I write it that way because this is using the information from the problem. We have 11 characters up here, and we have 7 characters there. And so basically, whenever you have 11 spots to fill, and 7 spots to fill, and 11 characters to use to fill those spots, then this is the number that you get, and that the fancy mathematical word we use for that is permutation, and we put a P there. Permutation means just ways of permuting things, ways of rearranging things. Basically, you're thinking of all the ways you can rearrange these numbers here by having different ones come first. So to permute something means to rearrange it, and so the way we write this is P with an 11 there and a 7 there. So this is permutations. Okay? So P 11, 7 means basically we had 11 to choose from and we're filling 7 spots. And so how many different ways are there to do it? Assuming no repeats, it's going to be 11 factorial divided by 11 minus 7 factorial, and that'll give you that. Okay, very good. How are we doing here? Very good. Okay, now let's look at one other problem, which is similar to this one, but very different. Okay, we have those same 11 characters again, and we're going to choose 7, but this time, instead of thinking of it as a license plate, let's think of it as a hand of cards. Okay, a hand of cards. So a 7, let's call it a 7-card hand. A 7-card hand from an 11-card deck. And the question is, how many? Okay? How many 7-card hands? How many 7-card hands from an 11-card deck? Okay? So again, just to be clear, you've got a deck with 11 cards, okay? Here they all are. Think of these as cards now. Each of these things is a card. Okay? There's your total deck. There's your total deck of cards right there. And shuffle them all up, and I draw 7 of them. And the question is, now I have 7 of these 11. How many different hands are possible? So here's the key question. How does this question differ from the previous one? Okay, notice that we're each starting with 11. We're each choosing 7. And in both cases, there's no repeats, right? Because you only have one of these cards. So if you choose H, you can't choose it again. You can only have one H in your deck, in your hand. Okay. So how do these compare with these? Well, let's think about it. I could have, for example, I could have a hand with, let me start here. I could have a license plate with A, B, C, D, E, F, G. There's 7 of them. I could have a license plate like that. I could also have a license plate like this, Let me start with B this time. B, C, D, E, F, G, A. There's another license plate I could have. Here's another one I could have. D, E, F, C, B, A, G. I mean, you could put them in any order, right? You could put them in any order. So all of these things are different license plates, all using just these letters. They're all different license plates, but do you agree that they're all the same hand? Right? Because when you have a hand, it doesn't matter what order they're in, it's still the same hand. If this hand is the same as this one's the same as this. They're all the same. You can rearrange them any way you want. They're still the same hand. So do you agree that you're going to have a lot more license plates than you're going to have hands? Because these are all just one hand, but they're three different license plates. See that? It's one hand, but a whole bunch of different license plates. So the real question we have to ask is, how many license plates can we get from just one hand? Well, let's think about it. If you have a hand with A through G, how many license plates could you make from just this particular hand? You've got 7 of them there. You've got 7 different characters. Now that I have my hand of cards, it's kind of like the original question now. Now that I have my hand of cards, how many different license plates could I make just of this hand? I'd have 7 different choices here, then 6 different here, 5 here, 4 here, 3 here, 2 here, and then finally my last one. Make sure that I'm still on here. Okay, I am good. Okay, you see that? So you have this many more license plates than you do hands, because from every hand you can make this many license plates. See that? You've got this many more license plates than you do hands, because from this one hand you can make all these license plates. So in other words, if I already know how many license plates I have, the way to get the number of hands is by dividing this number by this number, and that'll give me the number of hands. So the number of hands is going to be 11 factorial divided by 11 minus 7 factorial, which is what we had here, but I also have to divide it by this number, which is 7 factorial. Okay? So there it is right there. And whereas this is called the number of permutations, the number of ways you can arrange things, this is called the number of combinations. You're not interested in the order, you're just interested in how many combinations there are, just like a hand of cards. And so we use the mathematical symbol C with an 11 there and a 7 there to stand for combinations. Again, I don't have enough room to write the whole thing out. Okay, combinations. And so there it is right there. And if you calculate this, which we can do by taking this number right here and dividing it by 7 factorial, then we get, I just did it, 330. Rather amazing, 330. So it's kind of amazing. It's amazing to me that if you take you start with 11 characters and you have a list of 7 of them where you can allow repeats, then you have almost 20 million various possibilities. If you have the same 7 places to fill, but now you do not allow repeats, then it goes from 19.5 million down to roughly 1.5 million. So it drops down considerably. And then if you not only don't allow repeats, but also you don't care what the order is. So now you think of it as a hand of cards rather than as a license plate. Then you divide by the 7 factorial and you end up with only 330. So drops down a whole lot. So anyway, as I mentioned, a lot of counting problems are basically using one of these 3 ideas and kind of combining them, that sort of thing. So you'll be asked to do this in one of your CEPs. So now you know Now you know what you need to know. Very good. Next time we'll work on probability.